Hello, and welcome to a world of shimmering white, a realm of breathtaking beauty and profound mystery, the world of ice. Imagine, if you will, a colossal glacier, a river of ice stretching as far as the eye can see, its surface a tapestry of sapphire and white, etched with the deep wrinkles of time. Picture a snowflake, a tiny masterpiece of crystalline perfection, each one unique, a fleeting whisper of winter's magic. This is the world we're about to explore, a world sculpted by freezing temperatures, shaped by immense forces, and intimately connected to the very pulse of our planet. For centuries, ice has captivated humankind. From the awe-inspiring grandeur of polar ice caps to the delicate artistry of frost on a window pane, ice holds a unique place in our collective imagination. But beyond its aesthetic appeal lies a fascinating scientific story, a story woven from the intricate dance of water molecules, the relentless march of glaciers, and the delicate balance of our climate system. Over the next hour and a half, we'll unravel the secrets of ice, exploring its formation, its properties, its impact on our world, and its crucial role in shaping the future of our planet. We'll journey from the microscopic world of ice crystals, examining their complex structures and the surprising ways they behave, to the majestic scale of glaciers and ice sheets, understanding their immense power to shape landscapes and influence sea levels. We'll delve into the science of snow, exploring the fascinating process of snowflake formation and the vital role snow plays in our global water cycle. And we'll confront the urgent realities of climate change, investigating how the melting of ice is altering our planet and what we can do to protect this precious resource. This isn't just a journey into the science of ice. It's a journey into understanding our planet, its delicate ecosystems, and the profound impact human activity has on the natural world. So, settle in, relax, and prepare to be amazed by the wonders of ice. A substance so familiar yet so profoundly mysterious. A substance that holds the key to understanding our past, present, and future. Our exploration begins now with a closer look at how ice, in all its forms, comes to be. Let's delve into the fascinating science that underpins this frozen world. Prepare to be captivated by the beauty and power of ice. A story told in frost, snow, and the silent grandeur of glaciers. Our journey through the science of ice begins. Now that we've set the stage, let's delve into the fundamental science behind ice itself. It all starts with water, the very essence of life. But water isn't just a simple molecule. It's a remarkably complex and dynamic substance, and its behavior at freezing temperatures is particularly fascinating. Imagine those tiny water molecules, each composed of two hydrogen atoms bonded to a single oxygen atom. At room temperature, they zip around like energetic toddlers, constantly jostling and bumping into each other. But as the temperature drops towards 0 degrees Celsius or 32 degrees Fahrenheit, something remarkable happens. The molecules begin to slow down, their kinetic energy decreasing. This allows the attractive forces between them to take hold. These forces cause the water molecules to arrange themselves into a highly ordered, crystalline structure, the familiar hexagonal pattern we associate with ice crystals. Each molecule forms weak hydrogen bonds with its neighbors, creating a lattice-like framework that extends throughout the ice. This precise arrangement is what gives ice its unique properties. And here's where things get really interesting. Unlike most substances, which become denser as they freeze, water actually becomes less dense. This is because the hexagonal structure of ice crystals creates more space between the molecules compared to liquid water. This density anomaly is crucial for life on Earth. If ice were denser than water, it would sink to the bottom of lakes and oceans, leading to a complete freezing over and potentially devastating consequences for aquatic life. Think about it, the fact that ice floats acts like a natural insulator, protecting the water below from freezing solid. This allows aquatic ecosystems to survive even in the harshest winters, a testament to the remarkable properties of water and the intricate balance of nature. So, the next time you see a sheet of ice, remember that you're witnessing a truly extraordinary transformation, a testament to the remarkable physical properties of water, a transformation that has profound implications for life on our planet. Understanding this fundamental transformation is crucial to understanding the larger world of ice we're exploring today. This is just the beginning of our deep dive into the fascinating science of ice. We'll continue to explore its many wonders, from its intricate crystalline structures to its role in shaping our planet's climate. Now that we understand how water transforms into ice, let's zoom in and examine the exquisite architecture of ice crystals themselves. Remember those hexagonal structures we discussed? They're far more than just a simple geometric pattern. They're the key to understanding many of ice's unique properties. Imagine each water molecule as a tiny building block, carefully interlocking with its neighbors through those weak hydrogen bonds. This creates a remarkably intricate three-dimensional lattice, a framework that extends throughout the entire ice crystal. The hexagonal shape isn't just a random occurrence. It's a direct consequence of the way water molecules bond with each other, a testament to the elegance of nature's design. This hexagonal structure is responsible for many of ice's characteristics, including its fascinating fragility. Those hydrogen bonds, while crucial for holding the structure together, are relatively weak compared to other chemical bonds. This explains why ice can be so easily shattered, why a seemingly solid sheet of ice can crack underfoot, and why glaciers can calve, creating breathtaking yet powerful displays of nature's raw force. But the hexagonal structure isn't just about fragility. It's also responsible for ice's remarkable ability to reflect and refract light. The precise arrangement of water molecules within the crystal lattice causes light to scatter and bend in fascinating ways. This is why snow-covered landscapes appear so brilliantly white, reflecting sunlight back into the atmosphere. It's why glaciers shimmer with an ethereal blue, a color created by the absorption and scattering of light within the ice's crystalline structure. The intricate details of this structure are still being uncovered by scientists. Advanced imaging techniques continue to reveal new insights into the subtle variations in ice crystal formation, influencing everything from the delicate patterns of snowflakes to the immense strength and resilience of glacial ice. The beauty of ice is more than skin deep. It's a reflection of the intricate, elegant design of its crystalline structure. This underlying structure, this perfectly ordered arrangement of water molecules, is the foundation upon which all the other properties of ice are built. And as we continue our journey through the science of ice, we'll see how this fundamental structure influences everything from the formation of snowflakes to the dynamics of vast ice sheets. We're only beginning to scratch the surface of this fascinating topic. Let's move on to explore another captivating aspect of the world of ice. We've touched upon the fascinating fact that ice is less dense than liquid water, a truly remarkable anomaly in the world of materials. But let's delve deeper into the profound implications of this unique property. Why is it so significant that ice floats? The answer lies in the survival of aquatic life and the overall health of our planet's ecosystems. Imagine a world where ice was denser than water. As lakes and oceans began to freeze, the newly formed ice would sink to the bottom, creating a chilling cascade effect. Layer upon layer of ice would accumulate at the depths, eventually freezing entire bodies of water solid. This would have catastrophic consequences for aquatic organisms, wiping out entire ecosystems and fundamentally altering the balance of life on Earth. But because ice floats, it acts as a natural insulator, creating a protective layer on the surface of lakes and oceans. This layer prevents the water below from freezing solid, allowing aquatic life to survive even in the harshest winter conditions. This seemingly simple phenomenon is a testament to the delicate balance of nature, a crucial element in maintaining the biodiversity of our planet's aquatic environments. The fact that ice floats is not just a scientific curiosity. It's a fundamental principle that underpins the viability of countless aquatic ecosystems. Now, let's turn our attention to another fascinating aspect of ice's interaction with light. We've already discussed how the crystalline structure of ice causes it to reflect light, giving snow its brilliant white appearance. But the interaction between ice and light is far more complex and captivating than that. Have you ever witnessed the stunning display of a rainbow arcing across a snow-covered landscape? Or seen the mesmerizing shimmer of a glacier's surface, its blue hues shifting and dancing in the sunlight? These captivating phenomena are a direct result of how ice interacts with light. The intricate structure of ice crystals causes light to refract and scatter, creating a dazzling array of colors and patterns. The way light bends and reflects within the ice crystals depends on factors such as crystal size, orientation, and the angle of the incoming light. This intricate interplay of light and ice creates a visual spectacle, a reminder of the subtle yet powerful beauty of the natural world. The next time you witness the shimmering surface of a frozen lake or the vibrant colors of a rainbow against a snowy backdrop, take a moment to appreciate the underlying physics, the complex dance between light and ice that creates these breathtaking displays. These visual wonders are not just aesthetically pleasing. They're a testament to the intricate and fascinating properties of ice, a substance that plays a crucial role in shaping our planet and its ecosystems. Understanding these interactions is key to appreciating the full complexity and beauty of the world of ice. Imagine a still, clear lake on a crisp winter's evening. The air is biting, the stars are bright, and a delicate transformation is underway. The process of lake ice formation is a fascinating journey, a testament to the power of nature's subtle yet persistent forces. It all begins with the initial drop in temperature. As the water cools, it reaches a point where the molecules slow down enough to form those crucial hydrogen bonds we've discussed. Tiny ice crystals begin to form, often clinging to submerged vegetation or other irregularities on the lake bed. These nascent crystals act as seeds, attracting more and more water molecules, slowly growing in size and number. These initial crystals aren't the solid, smooth ice we typically envision. They're more like delicate, fragmented structures, a network of interconnected ice shards. As the temperature continues to fall, these crystals expand and coalesce, gradually forming a thin layer of slush across the lake's surface. This fragile layer, often referred to as frazzle ice, is easily broken and rearranged by wind and currents. But as the cold persists, the frazzle ice thickens and consolidates, forming a more robust and cohesive ice sheet. The process is far from uniform. Pockets of slush may persist, and the ice sheet itself might be uneven in thickness. The final result is a seemingly solid surface, a frozen mirror reflecting the night sky. Yet beneath this seemingly tranquil surface, the intricate processes of ice formation continue. Several factors influence the thickness and stability of this frozen sheet. The duration and intensity of the cold spell are crucial, as is the depth and flow of the underlying water. Shallow lakes tend to freeze over more quickly and completely than deeper ones, while currents and wind can create areas of thinner ice or even open water within the ice sheet. Understanding these factors is critical for safe winter recreation on lakes and for assessing the overall health of lake ecosystems. The formation of lake ice is not just a physical process. It has profound ecological implications. The ice sheet itself provides habitat for various organisms, while also influencing the temperature and oxygen levels of the water below. The insulating effect of the ice layer, as we've already discussed, is vital for the survival of aquatic life during winter months. As the ice melts in spring, the release of nutrients and oxygen further contributes to the lake's overall productivity. The seemingly simple act of a lake freezing over is, in reality, a complex event with far-reaching consequences for the entire lake ecosystem. It's a reminder of the intricate interconnectedness of nature, where even the most seemingly mundane processes play a vital role in maintaining the delicate balance of life. And as we continue our exploration of the science of ice, we'll uncover even more of its captivating secrets. Now, let's journey to a realm of colossal scale and breathtaking beauty, the world of glaciers. These magnificent rivers of ice, sculpted over millennia, are powerful agents of change, shaping landscapes and influencing global climate patterns. Their formation is a testament to the enduring power of snow and the relentless force of gravity. The story begins high in the mountains, or in polar regions, where snowfall accumulates year after year. Each individual snowflake, a tiny crystalline marvel, contributes to a growing blanket of snow. As more snow falls, the weight of the overlying layers compresses the snow below, forcing out air and increasing its density. This transformation from fluffy snow to dense, granular snow, known as firn, is a crucial step in glacier formation. The process continues as more snow accumulates. The firn is further compressed, its individual crystals merging and recrystallizing into larger, more compact ice crystals. This gradual compaction continues until the ice becomes so dense and thick that it begins to flow under its own weight, a slow, creeping movement that shapes the glacier's form. Glaciers are not static entities. They are dynamic systems constantly in motion. Gravity is the driving force, pulling the massive ice sheet downhill, often carving deep valleys and shaping mountain ranges in the process. This movement is slow, often measured in centimeters per day, but over centuries and millennia, the cumulative effect is dramatic. The erosional power of glaciers is immense. As they move, they pick up rocks and debris, acting like colossal sandpaper, grinding away at the underlying rock surface. This process, known as abrasion, creates distinctive features such as U-shaped valleys, polished rock surfaces, and the characteristic striations that indicate the direction of glacial flow. The debris carried by glaciers, known as glacial till, is deposited as the glacier melts, creating moraines, long ridges of sediment that mark the glacier's former extent. These ancient rivers of ice are not just agents of erosion. They are also powerful sculptors of landscapes. The features they create, the deep valleys, the sharp peaks, the fertile plains, are a testament to their immense power and enduring influence. The landscapes sculpted by glaciers are often breathtakingly beautiful, a testament to the slow, steady work of nature over vast spans of time. Studying glaciers, therefore, isn't just about understanding ice. It's about understanding the profound forces that shape our planet and the legacies they leave behind in the landscapes they carve. And as we continue our exploration, we'll delve into the crucial role glaciers play in our planet's climate system and the urgent challenges they face in a changing world. Let's shift our focus from the monumental scale of glaciers to the exquisite detail of individual snowflakes. Each snowflake, a tiny masterpiece of ice, is a unique testament to the intricate processes occurring high in the atmosphere. While they all share the fundamental hexagonal structure dictated by the arrangement of water molecules, the sheer diversity of snowflake shapes is astonishing. No two snowflakes are exactly alike, a fact that has captivated scientists and artists for centuries. This uniqueness arises from the complex interplay of atmospheric conditions during their formation. As water vapor rises into the colder upper atmosphere, it undergoes a phase transition, transforming from a gas into a solid. This process typically begins around -10 degrees Celsius, though the exact temperature depends on various factors like air pressure and the presence of other particles. The initial ice crystal forms around a tiny particle, such as a speck of dust or pollen, acting as a nucleation site. As more water molecules attach to this nucleus, the crystal grows, its shape dictated by the prevailing atmospheric conditions. Temperature plays a crucial role, influencing the rate at which water molecules attach to the crystal and the orientation of their bonds. Humidity also plays a significant part, determining the availability of water vapor for crystal growth. The shape of a snowflake evolves as it falls through the atmosphere, encountering varying temperatures and humidity levels along its journey. These changes influence the rate of growth on different faces of the crystal, creating complex branching patterns and intricate details. A snowflake's journey through the atmosphere is a dynamic process, with its growth constantly adapting to the ever-changing environment. The beauty of a snowflake lies in its symmetry, a reflection of the underlying crystalline structure of ice. The six-fold symmetry is a direct consequence of the hexagonal arrangement of water molecules, a fundamental property that governs the growth pattern of the ice crystal. But within this fundamental symmetry, an incredible variety of shapes and patterns can emerge, giving rise to the breathtaking diversity we observe in snowflakes. Imagine a snowflake falling through a cloud, constantly accumulating more ice molecules. The subtle variations in temperature and humidity it encounters along its path create unique growth conditions on each facet of the crystal. This leads to complex branching, intricate patterns, and the overall unique shape of each snowflake. It's a mesmerizing dance between temperature, humidity, and the inherent properties of water molecules, resulting in these exquisite, ephemeral works of art. The next time you see a snowflake, take a moment to appreciate the intricate journey it has undertaken, the complex processes that have shaped its form, and the fleeting beauty it embodies. It's a tiny microcosm of the broader wonders of the science of ice. Now, let's venture to the frigid realms of the Arctic, where the ocean itself freezes, transforming into a vast, dynamic landscape of sea ice. This isn't just frozen seawater. It's a complex ecosystem, a vital component of the Arctic's climate system, and a critical habitat for a unique array of wildlife. Sea ice formation begins with a subtle shift in the ocean's surface temperature. As the air temperature drops below freezing, the surface water begins to cool. Tiny ice crystals, known as frazzle ice, form within the water column, eventually accumulating to form a slushy layer known as grease ice. As the process continues and temperatures plummet further, these crystals coalesce, forming thin sheets of ice that gradually thicken and expand. The growth of sea ice is a continuous process, influenced by a variety of factors including air temperature, salinity, and wind. The salinity of the seawater plays a critical role, as the freezing of seawater rejects salt, creating a layer of brine that remains trapped within the ice. This brine, however, eventually drains out, leaving behind a more pure form of ice. The thickness of the sea ice can vary significantly, from thin, fragile ice to thick, multi-year ice that has survived multiple melt seasons. Sea ice plays a crucial role in regulating the Earth's climate. Its high albedo, or reflectivity, means that it reflects a significant amount of incoming solar radiation back into space, helping to keep the Arctic cool. This reflectivity contrasts sharply with the darker ocean water, which absorbs much more solar radiation. The extent of sea ice cover, therefore, significantly influences the amount of heat absorbed by the Arctic Ocean and the surrounding atmosphere. Furthermore, sea ice significantly impacts the salinity of the Arctic Ocean. As sea ice forms, it rejects salt, increasing the salinity of the surrounding water. This process helps to drive ocean currents and influence global ocean circulation patterns. The intricate interplay between sea ice, ocean currents, and atmospheric conditions is a complex system that profoundly influences the global climate. The Arctic ecosystem is intimately linked to sea ice. The underside of the ice provides a habitat for a vast array of algae, which form the base of the Arctic food web. These algae, in turn, support a rich community of zooplankton, small fish, and larger marine mammals such as seals and polar bears. Sea ice serves as a hunting platform for polar bears, a critical breeding habitat for seals, and a migratory pathway for many Arctic birds. The decline in sea ice extent due to climate change is therefore a cause for serious concern, threatening the delicate balance of this unique ecosystem. The fate of the Arctic's frozen ocean is inextricably linked to the health of our planet. Picture this: a vast, frozen expanse stretching to the horizon, a world sculpted by ice, where the sun dips low, casting long shadows across a breathtaking landscape. This is the Arctic, a realm of breathtaking beauty and unparalleled ecological significance, where the fate of countless creatures is inextricably linked to the presence of sea ice. Sea ice isn't just a frozen surface. It's a dynamic ecosystem, a vibrant habitat teeming with life. Beneath its icy surface lies a hidden world, a haven for microscopic algae, the foundation of the Arctic food web. These tiny plants, thriving in the frigid waters, provide sustenance for countless zooplankton, small crustaceans, and other invertebrates. These, in turn, become the primary food source for larger creatures. Consider the majestic polar bear, the undisputed king of the Arctic. These magnificent predators rely heavily on sea ice for hunting. Their primary prey, seals, utilize the ice floes as breeding grounds, resting areas, and escape routes from predators. The ice provides the platform from which polar bears stalk their prey, patiently waiting for an opportunity to ambush unsuspecting seals at their breathing holes. The decline in sea ice directly threatens the survival of polar bears, impacting their ability to hunt effectively and ultimately jeopardizing their populations. Seals themselves are not immune to the changing conditions. The loss of sea ice reduces the availability of suitable breeding and resting areas, making them more vulnerable to predators and environmental stressors. Harp seals, ringed seals, and bearded seals all depend on sea ice for various aspects of their life cycle, from breeding and puppying to molting and resting. A decline in sea ice translates to a decline in their populations, disrupting the delicate balance of the Arctic ecosystem. Beyond polar bears and seals, numerous bird species rely on sea ice for survival. Many seabirds, including gulls, kittiwakes, and auks, depend on the ice for foraging opportunities. The ice provides a platform for diving birds to hunt for fish and other prey. The loss of sea ice also affects the breeding success of many seabirds, as they rely on ice floes for nesting sites. The consequences of sea ice decline extend far beyond the immediate impact on individual species. The intricate web of life in the Arctic is interconnected, and the loss of sea ice ripples through the entire ecosystem. Changes in sea ice extend affect ocean currents, water temperatures, and nutrient cycling, impacting the entire food web and leading to cascading effects throughout the ecosystem. The decline in sea ice is a clear indicator of the profound changes occurring in the Arctic, a stark reminder of the urgent need for conservation efforts and climate action. The fate of this unique and irreplaceable ecosystem hangs in the delicate balance of the Arctic's frozen seas. Imagine towering peaks, their summits cloaked in pristine white, a landscape sculpted by the relentless power of ice and snow. This is the realm of mountain ecosystems, where glaciers and snowpack play a vital role in shaping the environment and supporting a unique array of life. These icy giants are far more than just beautiful features. They are the lifeblood of these high-altitude habitats. Glaciers, these slow-moving rivers of ice, act as natural reservoirs, storing vast quantities of water. As they melt, they release this precious resource, feeding streams and rivers that flow down into valleys and plains below. This meltwater sustains ecosystems far beyond the immediate vicinity of the glaciers themselves, providing crucial hydration for plants, animals, and human communities. The timing and rate of glacial melt influence the availability of water throughout the year, impacting everything from agriculture to hydroelectric power generation. Snowpack, the accumulated snow on mountain slopes, plays a similarly crucial role. It acts as a natural insulator, protecting the ground from extreme temperature fluctuations and preventing frost damage to vegetation. As the snow melts gradually during the warmer months, it provides a slow and steady release of water, replenishing rivers and sustaining ecosystems throughout the spring and summer. This natural water regulation is critical for maintaining biodiversity and supporting the livelihoods of communities that depend on mountain resources. The unique flora and fauna of mountain ecosystems are adapted to the harsh conditions of high altitude and the fluctuating water availability dictated by glacial melt and snowpack. Specialized plants have evolved to withstand freezing temperatures, strong winds, and limited soil nutrients. Animals, too, have adapted to these challenging conditions, developing strategies for survival in a landscape where resources are often scarce and unpredictable. Mountain goats, for example, are perfectly adapted to navigating steep, icy slopes, while the iconic snow leopard relies on the snowpack for hunting and camouflage. However, the delicate balance of mountain ecosystems is increasingly threatened by climate change. Rising global temperatures are causing glaciers to melt at an alarming rate, leading to changes in water availability and impacting downstream communities. Reduced snowpack diminishes the natural water storage capacity of mountains, increasing the risk of water shortages during dry periods. These changes are not only impacting the delicate balance of mountain ecosystems, but also threatening the livelihoods of the people who depend on them. The consequences of glacial melt extend far beyond the mountains themselves, affecting water resources, agriculture, and human settlements in downstream areas. The future of these magnificent ecosystems hangs in the balance, and it's vital that we understand and address the impacts of climate change on these precious mountain environments. Imagine drilling deep into the heart of a glacier, extracting a cylinder of ancient ice, a time capsule preserving millennia of Earth's history. These aren't just frozen chunks of water. They're ice cores, invaluable archives revealing secrets of our planet's past climate and environment. Scientists meticulously extract these cores from glaciers and ice sheets across the globe, unlocking a treasure trove of information about past temperatures, atmospheric composition, and environmental changes. The process of obtaining these ice cores is a fascinating undertaking, a blend of precision engineering and painstaking fieldwork. specialized drilling equipment, often designed to withstand the harsh conditions of polar regions, bores deep into the ice, extracting long, cylindrical samples. These cores are carefully retrieved, packaged, and transported to specialized laboratories for analysis. The entire process is meticulous, ensuring the integrity and preservation of the invaluable data locked within the ice. Each ice core is a layered record, with each layer representing a specific period in time. The deeper you go, the further back in time you travel. These layers aren't just visually distinct. They contain a wealth of information about the conditions under which they formed. Tiny air bubbles trapped within the ice preserve samples of the ancient atmosphere, offering a glimpse into the composition of the air from centuries or even millennia ago. Scientists can analyze the gases trapped within these bubbles, determining the concentrations of greenhouse gases like carbon dioxide and methane, vital indicators of past climate change. The isotopic composition of the water molecules within the ice provides another crucial piece of the puzzle. By analyzing the ratios of different isotopes of oxygen and hydrogen, scientists can reconstruct past temperatures with remarkable accuracy. These isotopic measurements reveal subtle variations in temperature over time, offering a detailed picture of past climate fluctuations. This information is critical for understanding the natural variability of Earth's climate and for discerning the impact of human activities on the current warming trend. Beyond temperature and atmospheric composition, ice cores also contain valuable information about past environmental changes. The presence of dust, pollen, volcanic ash, and other particles within the ice provides insights into past volcanic eruptions, changes in vegetation, and the transport of pollutants. These diverse data sources, combined with isotopic analysis and atmospheric measurements, provide a comprehensive picture of past environmental conditions. By piecing together this complex puzzle of information from ice cores, scientists can create detailed reconstructions of past climates, offering valuable insights into the dynamics of our planet's climate system and the potential impacts of future climate change. These invaluable ice core records are crucial for understanding the intricacies of our planet's past and for predicting the future course of our climate. They serve as a powerful testament to the enduring power of ice to preserve and reveal the secrets of our planet's history. Once these icy cylinders are carefully extracted from the depths of glaciers, the real detective work begins. Analyzing ice cores is a meticulous process, requiring sophisticated laboratory techniques and a keen eye for detail. Imagine peering into a microscopic world, where the secrets of the past are revealed through the analysis of tiny air bubbles and the precise measurement of isotopic ratios. One of the most crucial analyses involves measuring the isotopic composition of the water molecules within the ice. Water molecules are made up of oxygen and hydrogen atoms, but these atoms can exist in different isotopic forms. By carefully measuring the ratios of different oxygen and hydrogen isotopes, scientists can deduce the temperature at which the ice formed. Heavier isotopes tend to concentrate in ice formed at lower temperatures, offering a precise thermometer for past climates. This isotopic analysis provides a remarkably detailed record of temperature fluctuations over time, revealing subtle changes that might otherwise go unnoticed. Trapped within the ice are tiny air bubbles, each a microcosm of the ancient atmosphere. These bubbles offer a direct sample of the air from the time the ice formed. Scientists carefully extract these air bubbles and analyze their composition, measuring the concentrations of various gases, including carbon dioxide, methane, and other greenhouse gases. These measurements provide invaluable insights into the past atmospheric composition, revealing changes in greenhouse gas concentrations over time. This information is crucial for understanding the relationship between atmospheric composition and climate change. The combination of isotopic analysis and gas measurements paints a rich picture of past climates and environmental events. By comparing data from different ice cores across the globe, scientists can create a comprehensive reconstruction of past climate patterns, revealing regional and global variations in temperature and atmospheric composition. These reconstructions provide critical context for understanding the current climate change trends, allowing us to differentiate between natural climate variability and human-induced changes. But the information gleaned from ice cores extends beyond temperature and atmospheric composition. The presence of various particles within the ice, such as dust, pollen, volcanic ash, and even pollutants, provides further insights into past environmental events. Scientists can use this information to reconstruct past volcanic eruptions, track changes in vegetation patterns, and even determine the extent of past pollution. These diverse data sources, combined with isotopic analysis and gas measurements, create a comprehensive picture of past environmental conditions and the interplay of different factors shaping our planet's climate. Analyzing ice cores isn't just about understanding the past. It's about using this knowledge to better predict the future and make informed decisions about our planet's future. The intricate details revealed by these frozen archives provide invaluable insights for navigating the complexities of climate change and preserving the delicate balance of our Earth systems. Let's delve into the fascinating physics behind something we experience daily: the melting of ice. It's more than just a simple transition from solid to liquid. It's a captivating dance of energy and molecular rearrangement. Imagine those intricate ice crystals, each a masterpiece of organized water molecules, held together by a network of hydrogen bonds. These bonds, relatively weak compared to covalent bonds, are the key to ice's unique properties. When we add heat, whether from the sun's rays, ambient air, or a warm drink, energy is transferred to these ice crystals. This energy doesn't simply make the ice warmer. It disrupts the delicate hydrogen bond network. Think of it as adding energy to a perfectly choreographed dance. The dancers, water molecules, start to lose their synchronized movements, becoming less organized. As more energy is absorbed, the hydrogen bonds begin to break. This doesn't happen all at once. It's a gradual process. Individual water molecules gain enough kinetic energy to overcome the attractive forces holding them in their fixed positions within the crystal lattice. They start to wiggle and jiggle, transitioning from a rigid, ordered structure to a more fluid, chaotic state. This transition is what we perceive as melting. The ice doesn't instantly become liquid water. It goes through a phased transition, a gradual shift in the physical state of matter. The temperature remains constant at 0 degrees Celsius, 32 degrees Fahrenheit. During this phase transition, even though heat is continuously being added, all that added energy is used to break the hydrogen bonds, allowing the water molecules to escape their crystalline prison. Once all the hydrogen bonds are broken, the ice has completely melted into liquid water. The water molecules are now free to move around, interacting with each other through weaker, more dynamic forces. This increased freedom of movement results in the characteristic fluidity of liquid water. The transition from the rigid structure of ice to the dynamic arrangement of liquid water is a beautiful example of how energy transfer affects the behavior of matter at a molecular level. Understanding the science of melting is not just an academic exercise. It's crucial for predicting the behavior of glaciers and ice sheets in a changing climate. The rate at which ice melts is directly related to the amount of energy absorbed, which is influenced by factors like air temperature, solar radiation, and ocean currents. Accurate modeling of ice melt requires a deep understanding of the energy transfer processes involved in this phase transition, allowing us to better predict sea level rise and the impacts of climate change on delicate ecosystems. The science of melting ice is a testament to the intricate interplay between energy, molecules, and the vast, dynamic systems of our planet. Imagine a world where coastal cities are increasingly threatened, where low-lying islands disappear beneath the waves, and where delicate coastal ecosystems are irrevocably altered. This isn't a dystopian fantasy. It's a potential future shaped by the melting of glaciers and ice sheets. The vast quantities of ice locked away in these frozen giants represent a significant volume of water, and their melting has profound implications for global sea levels. As temperatures rise due to climate change, glaciers and ice sheets begin to melt at an accelerated rate. This meltwater flows into the oceans, increasing the overall volume of water and causing sea levels to rise. The process isn't uniform. Some regions experience greater sea level rise than others due to factors like ocean currents and gravitational effects. But the overall trend is undeniable. Global sea levels are rising, and the melting of ice is a major contributing factor. The consequences of this sea level rise are far-reaching and potentially devastating. Coastal communities, home to millions of people worldwide, are particularly vulnerable. Rising sea levels lead to increased coastal erosion, more frequent and severe flooding, and saltwater intrusion into freshwater sources. This poses significant risks to infrastructure, livelihoods, and human safety. The displacement of coastal populations is a real and growing concern. Beyond the human impact, melting ice profoundly affects coastal ecosystems. Salt marshes, mangroves, and coral reefs, are vital habitats for countless species, are particularly sensitive to changes in sea level and salinity. Rising sea levels can inundate these ecosystems, leading to habitat loss and disrupting delicate ecological balances. The loss of these habitats can have cascading effects throughout the food web, impacting biodiversity and the overall health of marine environments. The rate of sea level rise is not constant. It's accelerating. As temperatures continue to increase, the melting of glaciers and ice sheets is expected to intensify, leading to even more rapid sea level rise in the coming decades. Understanding the dynamics of ice melt and its impact on sea levels is crucial for developing effective strategies to mitigate the risks and protect vulnerable communities and ecosystems. This requires a multifaceted approach, including reducing greenhouse gas emissions, improving coastal defenses, and developing adaptation strategies to help communities cope with the inevitable changes. The fate of our coastlines, and indeed the planet, depends on our ability to understand and address the challenges posed by melting ice. The future of our coastal communities and the health of our oceans hang in the balance. The urgency to act is clear. Imagine a vast, interconnected system, a delicate dance between ocean currents, atmospheric circulation, and the reflective surface of ice. This intricate system governs our global weather patterns, and changes in ice cover can dramatically disrupt this delicate balance. The impact of melting ice on weather patterns is far-reaching and complex, influencing everything from regional temperatures to the intensity of storms. One of the most significant ways ice affects weather is through its influence on ocean currents. Vast expanses of sea ice in the Arctic and Antarctic play a crucial role in regulating ocean temperature and salinity. Sea ice formation, a process of freezing seawater, rejects salt, increasing the salinity of the surrounding water. This denser, saltier water sinks, driving deep ocean currents that redistribute heat around the globe. As sea ice melts, this process is disrupted, potentially altering the strength and pathways of these crucial currents. Changes in ocean currents can lead to significant shifts in regional temperatures and precipitation patterns. Furthermore, ice cover plays a critical role in regulating atmospheric circulation. Ice and snow have high albedo, meaning they reflect a significant portion of incoming solar radiation back into space. This reflectivity helps to regulate global temperatures and prevents excessive warming. As ice cover decreases, less solar radiation is reflected, leading to increased absorption of heat by the Earth's surface and atmosphere. This can amplify warming trends and further accelerate the melting of ice, creating a feedback loop. The resulting changes in atmospheric pressure and temperature gradients can alter wind patterns and storm tracks, potentially leading to more frequent and intense extreme weather events. The impact of melting ice on weather patterns is not uniform across the globe. Some regions may experience increased warming, while others might see changes in precipitation patterns, leading to droughts or floods. These regional variations in climate are driven by complex interactions between changes in ocean currents, atmospheric circulation, and the albedo effect. Understanding these interactions is crucial for predicting future climate scenarios and developing strategies to adapt to the changing weather patterns. The study of melting ice and its impact on weather patterns is an ongoing area of research. Scientists are using sophisticated climate models and observational data to better understand these complex interactions and improve predictions of future climate change. The more we learn about the role of ice in our climate system, the better equipped we will be to address the challenges posed by a changing world. The consequences of ignoring these changes are potentially dire, highlighting the importance of continued research and global cooperation in addressing this critical issue. Picture this: a pristine, snow-capped mountain range, its glaciers slowly releasing meltwater into rivers that nourish downstream ecosystems. This seemingly simple process is fundamental to the health of countless ecosystems around the world, but the accelerating pace of ice melt is disrupting this delicate balance with far-reaching consequences. The effects cascade through various ecosystems, impacting freshwater availability, food webs, and habitats, threatening biodiversity and the services these ecosystems provide. One of the most immediate impacts of melting ice is the alteration of freshwater availability. Glaciers and snowpack act as natural reservoirs, storing water during colder months and releasing it gradually throughout the year. This regulated flow of freshwater is crucial for agriculture, drinking water supplies, and the maintenance of healthy river ecosystems. As glaciers shrink and snowpack diminishes, the timing and volume of freshwater release are disrupted, leading to water shortages during dry seasons and increased flood risks during periods of rapid melt. This instability directly impacts human populations and the delicate balance of aquatic ecosystems that rely on a consistent flow of fresh water. The disruption of freshwater availability cascades through food webs, affecting various species that depend on these water sources. Changes in water temperature, flow rate, and nutrient levels can drastically alter the composition and abundance of aquatic plants and animals, impacting fish populations and the organisms that prey upon them. This ripple effect can have significant consequences for larger ecosystems, leading to declines in biodiversity and ecosystem services. The interconnectedness of species within these ecosystems highlights the vulnerability of the entire food web to changes in freshwater availability. Beyond freshwater ecosystems, melting ice leads to significant habitat loss. Many species, particularly those adapted to cold environments, depend on ice and snow for survival. The decline of glaciers and sea ice is causing habitat loss for polar bears, seals, and various other species that rely on these icy habitats for breeding, feeding, and resting. The loss of these habitats forces animals to adapt, migrate, or face extinction, drastically altering the biodiversity of these regions. The changes occurring in these icy realms serve as a stark reminder of the far-reaching consequences of ice melt. The interconnectedness of these effects emphasizes the intricate relationship between ice melt and ecosystem health. The disruption of freshwater availability, changes in food webs, and habitat loss are not isolated events. They are intertwined processes that create a cascading effect throughout various ecosystems. Understanding these complex interactions is critical for developing effective strategies to mitigate the impacts of climate change and protect the biodiversity of our planet. The future of these ecosystems hinges on our ability to address the root causes of ice melt and to support the resilience of these vital environments. For centuries, ice has held a powerful place in the human imagination, woven into the fabric of myths, legends, and folklore across diverse cultures. Its transformative power, its ability to both preserve and destroy, has inspired awe and fear in equal measure, shaping our understanding of the world and our place within it. Let's journey through some of these captivating stories and explore the diverse ways in which different cultures have perceived and interpreted this fascinating substance. In many Northern European traditions, ice is often associated with powerful, often ambivalent deities. Think of the frost giants of Norse mythology, beings of immense strength and unpredictable nature, their icy domains reflecting the harsh realities of a winter landscape. These figures, sometimes benevolent, sometimes destructive, embody the power and unpredictability of winter's grip. Their stories highlight the respect and caution with which people approached the frozen world, acknowledging its capacity for both beauty and devastation. Moving further east, we find different interpretations in the folklore of Siberia and other Arctic regions. Here, ice often takes on a more spiritual significance, representing the boundaries between the living and the dead, the seen and the unseen. Tales of spirits inhabiting frozen lakes and glaciers, or of journeys undertaken across treacherous ice to the underworld, illustrate the spiritual depth associated with ice in these cultures. The icy landscapes are not just physical environments, but portals to other realms, rich with symbolic meaning. In contrast to the often harsh depictions of ice in northern cultures, some traditions view ice with a more gentle, even nurturing perspective. Certain indigenous cultures in the Americas, for instance, see ice as a source of life, a vital resource that sustains their communities. Their stories often emphasize the intricate relationship between ice, water, and the cycles of nature, highlighting the importance of respecting and preserving these precious resources. These narratives underscore the deep connection between human survival and the careful stewardship of the natural world. The cultural significance of ice isn't confined to the past. Even today, ice continues to inspire artists, writers, and filmmakers, its captivating beauty and symbolic power resonating across various creative mediums. From the ethereal landscapes of winter paintings to the metaphorical use of ice in literature to represent fragility or permanence, ice remains a powerful source of inspiration, reflecting our enduring fascination with its unique properties and profound impact on our world. These diverse interpretations, spanning geographical locations and historical periods, demonstrate the enduring power of ice to capture the human imagination and shape our cultural narratives. The stories we tell about ice reflect not only our perceptions of the natural world, but also our deepest hopes, fears, and understanding of our place within it. From the breathtaking landscapes captured on canvas to the chilling metaphors woven into literary masterpieces, ice has long served as a powerful muse for artists and writers. Its inherent beauty, its capacity for both delicate fragility and immense destructive power, has captivated creative minds across centuries, inspiring a vast array of artistic expressions. Consider the stunning visual representations of ice in art. Think of the intricate detail of snowflakes, magnified to reveal their astonishing crystalline structures, a subject that has fascinated artists for centuries. Their work often captures the ephemeral beauty of a snowflake, its unique pattern a fleeting moment of perfection before it melts away. Similarly, the grandeur of glaciers and icebergs, their immense scale and sculpted forms, have inspired countless paintings, photographs, and sculptures, revealing the raw power and majestic beauty of nature's icy creations. These works not only showcase the physical attributes of ice, but also evoke a sense of awe and wonder at the forces that shape our planet. Moving beyond the purely visual, we find ice's symbolic presence deeply embedded in literature. Ice often serves as a potent metaphor, representing various concepts depending on the context. It can symbolize coldness, emotional detachment, or the passage of time, freezing moments in history or relationships. In some works, ice acts as a barrier, a formidable obstacle that characters must overcome, reflecting the challenges and hardships faced in life. Conversely, it can also represent purity, innocence, or a pristine, untainted world. The versatility of ice as a literary symbol allows writers to explore a wide range of themes and emotions, enriching the narrative and deepening the reader's understanding. The use of ice in literature is not limited to metaphorical representations. It can also feature prominently in narratives, forming the backdrop for stories of survival, exploration, or even magical realism. Imagine the stark beauty of an Arctic landscape, the challenges of traversing icy terrains, or the suspenseful scenarios involving perilous ice flows. These settings often serve to heighten the drama, creating a unique atmosphere and contributing to the overall impact of the story. In these cases, ice is not merely a symbol. It is an integral part of the narrative itself. Beyond painting and literature, ice finds expression in other art forms as well. Music, dance, and film have all explored the themes and imagery associated with ice, capturing its unique aesthetic qualities and symbolic resonance. From the cold, haunting melodies that evoke the stillness of a frozen landscape to the graceful movements of dancers mimicking the fluidity of melting ice, artists across various disciplines continue to find inspiration in this fascinating natural phenomenon. These diverse artistic expressions collectively demonstrate the enduring power of ice to captivate our imagination and inspire creativity, reflecting our profound connection to the natural world and our ongoing exploration of its mysteries. Ice, in its myriad forms and interpretations, remains a timeless and powerful source of artistic inspiration. Long before the advent of modern refrigeration, humans ingeniously harnessed the natural properties of ice to preserve food and maintain cool temperatures. These early methods, often dictated by geography and available resources, reflect a remarkable adaptation to environmental conditions and a deep understanding of the practical applications of ice. In many parts of the world, naturally occurring ice, harvested from frozen lakes and rivers during winter, formed the basis of early ice preservation techniques. Imagine the scene. Communities gathering during the coldest months, carefully cutting and storing blocks of ice in insulated pits or cellars, often packed with sawdust or other insulating materials. This painstaking process ensured a supply of ice throughout the warmer months, allowing for the preservation of perishable goods like meat, fish, and dairy products. This ingenuity extended beyond simple storage. Ice houses, often elaborate structures designed to maximize insulation and minimize melting, became integral parts of many communities. These structures represented a significant step in food preservation technology, significantly expanding the availability of fresh food beyond the immediate growing season. The transportation of ice was another crucial aspect of its early uses. In regions where natural ice was abundant, the transport of ice to distant markets became a thriving industry. Early methods often involved the use of thick layers of insulating material, such as straw or sawdust, to protect the ice from melting during transit. This early cold chain logistics, though rudimentary by modern standards, played a vital role in expanding access to fresh food and other temperature-sensitive goods to populations far removed from natural ice sources. The economic and social impact of this early ice trade was substantial, shaping trade routes and contributing to the growth of urban centers. As human understanding of ice properties grew, so did the sophistication of its applications. The use of ice for medicinal purposes, for example, was widespread in many cultures. Ice packs were used to treat injuries and reduce inflammation, and the cooling effects of ice were believed to have therapeutic benefits for various ailments. While these practices lacked the scientific rigor of modern medicine, they demonstrate a practical understanding of ice's therapeutic properties, reflecting the ingenuity of early medical practices. The transition from using natural ice to the development of artificial refrigeration represents a significant turning point in human history. The invention of mechanical refrigeration, a process that enabled the artificial production of ice on a large scale, revolutionized food preservation, medicine, and various industries. This technological leap marked the beginning of a new era, enabling the transportation and storage of perishable goods across vast distances, maintaining consistent food quality and safety, and paving the way for a wide range of advancements in modern society. The journey from harvesting natural ice to creating it artificially reflects humanity's continuous quest to harness the power of nature and adapt it to meet our evolving needs. From the thrill of a downhill ski run to the quiet contemplation of ice skating on a frozen pond, ice plays a significant role in our modern recreational lives. Winter sports, a global phenomenon, rely entirely on the presence of ice and snow. Millions partake in activities like skiing, snowboarding, ice hockey, figure skating, and curling, showcasing the diverse ways in which we engage with this frozen landscape. These activities not only provide physical exercise and enjoyment, but also foster a sense of community and shared experience, bringing people together from all walks of life. The economic impact of winter sports tourism is substantial, supporting businesses and communities reliant on the seasonal influx of visitors. Beyond recreational pursuits, ice plays a crucial role in a surprising number of industries. The food and beverage industry, for instance, heavily relies on ice for cooling and preservation. From the ice cubes in our drinks to the sophisticated refrigeration systems used in food processing and distribution, ice ensures the quality and safety of the food we consume daily. The medical field also depends on ice for various applications, ranging from cryotherapy treatments to the preservation of biological samples. The controlled application of ice in medicine offers a range of therapeutic benefits, contributing to patient care and medical research. The construction industry utilizes ice in unique and often unexpected ways. In some regions, ice is used as a construction material, showcasing its surprising structural capabilities. Temporary ice structures, such as ice hotels and ice sculptures, demonstrate the versatility of ice as an architectural medium. These transient structures, though ephemeral, offer a unique and captivating experience for visitors. In addition, the study of ice's properties is crucial for understanding the effects of frost and ice formation on infrastructure, guiding the design and maintenance of buildings and transportation systems in cold climates. The energy sector also intersects with the world of ice in interesting ways. The potential for harnessing hydropower from glacial meltwater is being increasingly explored, representing a sustainable energy source in certain regions. Furthermore, the study of ice and snow cover is crucial for understanding climate change and its impact on global energy resources. The intricate relationship between ice and energy reveals how seemingly disparate aspects of our world are interconnected, highlighting the importance of a holistic approach to understanding our planet's systems. Scientific research on ice continues to yield invaluable insights into climate change, environmental monitoring, and various aspects of the natural world. The analysis of ice cores provides a rich historical record of climate patterns, atmospheric composition, and environmental changes, allowing scientists to reconstruct past climates and predict future trends. This research is crucial for understanding the impacts of climate change and developing effective mitigation and adaptation strategies. The study of ice is not merely a scientific pursuit. It is a vital tool for understanding and addressing the challenges facing our planet. As we continue to explore the intricacies of ice, we gain a deeper understanding of the complex processes that shape our environment and the importance of preserving its delicate balance. Picture this: a vast, shimmering expanse of white stretching to the horizon, a breathtaking landscape of Arctic sea ice. This frozen ocean, a critical component of Earth's climate system, is undergoing a dramatic transformation, a stark testament to the accelerating effects of climate change. The Arctic, often referred to as the world's refrigerator, is warming at a rate significantly faster than the global average, leading to a concerning decline in sea ice extent and thickness. Satellite data, meticulously collected over decades, paints a clear picture of this alarming trend. Summer sea ice minimums, once a stable feature of the Arctic landscape, are shrinking at an unprecedented pace. The once immense ice sheets, crucial for regulating global temperatures and reflecting sunlight back into space, are dwindling, revealing darker ocean waters that absorb more heat, creating a feedback loop that further accelerates the warming process. This isn't just a change in scenery, it's a fundamental shift in the Earth's climate engine. The consequences of Arctic sea ice loss extend far beyond the polar regions. As the ice melts, it contributes to rising global sea levels, threatening coastal communities and infrastructure worldwide. The altered ocean currents, influenced by changes in sea ice extent and salinity, can disrupt weather patterns, potentially leading to more frequent and intense extreme weather events in regions far removed from the Arctic. The melting ice also impacts the delicate balance of Arctic ecosystems, threatening the survival of countless species that depend on the sea ice for habitat, hunting, and breeding. Polar bears, walruses, and seals are just a few examples of the iconic animals facing increasing challenges in their struggle to adapt to this rapidly changing environment. Indigenous communities, who have lived in harmony with the Arctic environment for millennia, are on the front lines of this crisis. Their traditional ways of life, deeply intertwined with the sea ice, are being disrupted by the changes they are witnessing. The loss of sea ice affects their hunting practices, their access to resources, and their overall cultural heritage. Their intimate knowledge of the Arctic environment provides invaluable insights into the impacts of climate change and highlights the urgent need for action. Their stories are a powerful reminder of the interconnectedness of human societies and the natural world. The shrinking Arctic sea ice serves as a potent symbol of the broader climate crisis. It's a stark visual representation of the undeniable effects of human activities on our planet. The scientific evidence is irrefutable, and the urgency for global cooperation to mitigate climate change is paramount. Addressing this challenge requires a multifaceted approach, involving reductions in greenhouse gas emissions, sustainable resource management, and international collaboration to protect this vital ecosystem. The fate of the Arctic is inextricably linked to the future of our planet, and the time for decisive action is now. The story of the Arctic sea ice is a story of both profound beauty and urgent warning. It's a story that demands our attention, urging us to act before it's too late. Imagine colossal rivers of ice, slowly but relentlessly carving their way through mountains, shaping landscapes over millennia. These are glaciers, majestic monuments of nature, and they are vanishing before our eyes. The impact of climate change on glaciers worldwide is undeniable, a stark reminder of the planet's shifting climate. From the towering peaks of the Himalayas to the icy plains of Patagonia, glaciers are shrinking at an alarming rate, their retreat leaving behind a trail of environmental and societal consequences. The warming atmosphere is the primary culprit. Rising global temperatures cause glaciers to melt at an accelerated pace, contributing significantly to rising sea levels. This isn't just a gradual process. It's a dramatic shift, with many glaciers experiencing unprecedented melt rates in recent decades. Scientists meticulously monitor glacier mass balance, measuring the difference between snow accumulation and ice melt, providing a clear indication of their health and stability. The data paints a concerning picture: a widespread and accelerating decline in glacial ice. The effects extend far beyond the immediate vicinity of the glaciers themselves. As glaciers shrink, they reduce the availability of freshwater resources for communities that rely on glacial meltwater for drinking, irrigation, and hydropower generation. In many parts of the world, glaciers act as natural reservoirs, providing a steady supply of water throughout the year. Their dwindling size threatens the water security of millions, leading to potential water shortages and conflicts over dwindling resources. The loss of glacial ice also impacts downstream ecosystems, altering river flows and affecting the biodiversity of aquatic habitats. The intricate balance of nature, finely tuned over centuries, is being disrupted by the rapid changes in glacial dynamics. Furthermore, the melting glaciers contribute to the instability of mountain slopes, increasing the risk of landslides and glacial lake outburst floods, GLOFs. These catastrophic events can cause significant damage to infrastructure and communities located downstream. The potential for such events is amplified by the changing climate, creating a cascade of environmental hazards that threaten human lives and livelihoods. The melting glaciers aren't just a visual symbol of climate change. They represent a tangible threat to human safety and well-being. Understanding the dynamics of glacial melt is crucial for developing effective strategies to mitigate and adapt to the impacts of climate change. Scientists are employing a range of techniques, from remote sensing and ground-based measurements to sophisticated climate models, to study glacial behavior and predict future changes. This knowledge is essential for informing policy decisions and developing strategies to protect vulnerable communities and ecosystems. The story of the glaciers is a story of both awe-inspiring natural beauty and urgent environmental concern. It's a story that compels us to take action, reminding us of the fragility of our planet and the importance of preserving its delicate balance. Picture this: a vast, pristine wilderness of ice and snow, stretching as far as the eye can see. This is Antarctica, a continent of immense scale and profound ecological significance, and it's facing a critical threat: the relentless advance of climate change. The Antarctic ice sheet, a colossal reservoir of frozen water, holds enough ice to raise global sea levels by several meters if it were to melt completely. While a complete melt isn't expected in the near future, even a partial collapse could have devastating consequences for coastal communities worldwide. The Antarctic ice sheet isn't a monolithic entity. It's a complex system of interconnected glaciers, ice shelves, and floating icebergs, all responding differently to the warming climate. Warmer ocean waters, driven by climate change, are eroding the ice shelves from below, causing them to weaken and fracture. These ice shelves act as buttresses, holding back the flow of glaciers from the land into the ocean. Their disintegration accelerates the rate at which glaciers discharge ice into the sea, contributing to rising sea levels. This process is particularly concerning in West Antarctica, where the ice sheet is grounded below sea level, making it particularly vulnerable to the warming ocean. Scientists are closely monitoring the changes in Antarctic ice mass using a variety of techniques, including satellite observations, GPS measurements, and ice core analysis. These studies reveal a complex interplay of factors influencing the dynamics of the ice sheet, including changes in temperature, precipitation, and ocean currents. The data highlights the accelerating rate of ice loss, underscoring the urgency of addressing climate change to prevent catastrophic sea level rise. The sheer scale of the Antarctic ice sheet makes its potential contribution to future sea level rise a significant concern for the global community. The implications of significant Antarctic ice melt are far-reaching and profound. Coastal cities around the world would face increased risks of flooding and erosion, leading to displacement of populations and damage to infrastructure. Low-lying islands and coastal ecosystems would be particularly vulnerable, facing potential inundation and loss of habitat. The changes in ocean currents, driven by melting ice, could also disrupt weather patterns and marine ecosystems, creating a cascade of environmental consequences that ripple across the globe. Understanding the intricate processes driving Antarctic ice loss is crucial for predicting future sea level rise and developing strategies to adapt to its impacts. The fate of Antarctica is inextricably linked to the well-being of coastal communities and ecosystems across the planet. It's a story of immense scale, profound implications, and a critical need for collective action. The future of this icy continent holds the key to a stable future for many millions worldwide. Predicting the future of ice loss isn't simply a matter of guesswork. It's a complex scientific endeavor involving sophisticated computer models and a careful consideration of various scenarios. These models, built upon a deep understanding of physics, climate dynamics, and ice mechanics, simulate the intricate interactions between the atmosphere, ocean, and ice sheets. They incorporate factors such as temperature changes, precipitation patterns, ocean currents, and the flow of glaciers to project future ice loss under different emission pathways. Imagine these models as virtual laboratories, allowing scientists to experiment with different scenarios and explore potential outcomes. They run simulations based on various levels of greenhouse gas emissions, from moderate reductions to business-as-usual scenarios, allowing for projections ranging from relatively modest ice loss to more extreme and catastrophic melt events. These simulations are not just about crunching numbers. They're about creating a clearer picture of potential futures, allowing us to better understand the consequences of our actions. The models consider various feedback mechanisms, some of which can accelerate ice loss. For instance, as ice melts, the exposed land or darker ocean surface absorbs more solar radiation, leading to further warming and increased melting. This positive feedback loop amplifies the effects of climate change, making ice loss a self-reinforcing process. The models attempt to account for these complex interactions, although uncertainties remain regarding the precise timing and magnitude of future ice loss. The results of these models paint a range of possible futures, from relatively benign to profoundly disruptive. In more optimistic scenarios, where significant reductions in greenhouse gas emissions are achieved, ice loss might be slowed, reducing the severity of future impacts. However, in more pessimistic scenarios, where emissions continue to rise, the models project substantial ice loss, leading to significant sea level rise and widespread disruption of coastal ecosystems. This range of possibilities highlights the critical importance of mitigating climate change to minimize the potential risks associated with future ice loss. These models are not crystal balls, offering perfect predictions. They are sophisticated tools that provide valuable insights into potential futures, allowing us to assess the risks and plan for adaptation. The uncertainties inherent in these projections underscore the need for caution and the importance of proactive measures to reduce greenhouse gas emissions and prepare for the potential impacts of climate change. By understanding the range of possible outcomes, we can make more informed decisions about how to protect vulnerable communities and ecosystems from the consequences of a changing climate. The future isn't predetermined. It's a path we are actively shaping through our choices and actions today. The melting of vast ice sheets and glaciers isn't just a distant environmental concern. It's a potential catalyst for profound and widespread global changes. Imagine a world reshaped by rising sea levels, altered ocean currents, and disrupted ecosystems. This isn't science fiction. It's a real possibility if we fail to address the underlying causes of climate change. The most immediate and visible consequence of widespread ice melt is the rise in global sea levels. As colossal amounts of ice melt into the ocean, the volume of water increases, leading to inundation of coastal areas, erosion of shorelines, and increased risks of devastating floods. Low-lying islands and coastal communities face the most immediate threat, with potential for displacement and loss of homes, livelihoods, and cultural heritage. Even a modest rise in sea level can have far-reaching consequences, affecting millions of people worldwide. Beyond the direct impact of rising sea levels, the melting of ice sheets also disrupts ocean currents. These currents play a critical role in regulating global climate and distributing heat around the planet. The influx of fresh water from melting ice can alter the salinity and density of ocean waters, potentially disrupting the delicate balance of these currents. This disruption could lead to significant shifts in weather patterns, causing more extreme weather events, such as droughts, floods, and heat waves, in various parts of the world. The implications for global climate stability are immense. The impact on ecosystems is equally profound. Melting ice affects marine life, altering habitats and disrupting food webs. Changes in ocean temperature and salinity can lead to shifts in the distribution and abundance of marine species, affecting fisheries and impacting the livelihoods of those dependent on marine resources. Similarly, the melting of glaciers affects freshwater ecosystems, impacting river flows and the availability of freshwater resources for human consumption and agriculture. The consequences for biodiversity and the delicate balance of nature are significant. The potential consequences of widespread ice melt extend beyond the direct environmental impacts. The displacement of populations due to rising sea levels could lead to social unrest and migration, placing a strain on resources and infrastructure in affected regions. The economic impacts could be devastating, affecting coastal industries such as tourism, fishing, and shipping. The overall consequences are complex and interconnected, highlighting the urgent need for global cooperation to mitigate climate change and adapt to the unavoidable impacts of ice melt. Understanding the cascading effects of ice loss is crucial for developing effective strategies to protect vulnerable communities and ecosystems. The future of our planet depends on our collective response to this critical challenge. The fate of our planet's ice, and indeed the future of our climate, hinges on our collective ability to reduce greenhouse gas emissions. It's a simple truth, yet one that demands immediate and concerted action. The scientific consensus is clear. Human activities, particularly the burning of fossil fuels, are the primary driver of climate change, leading to the alarming rate of ice melt we're witnessing today. Reducing emissions isn't just about slowing the rate of ice loss. It's about safeguarding the future of our planet and ensuring a sustainable environment for generations to come. It's about mitigating the risks associated with rising sea levels, disrupted weather patterns, and the loss of biodiversity. It's about protecting coastal communities, preserving vital ecosystems, and ensuring the availability of freshwater resources. The transition to a low-carbon economy is a complex undertaking, requiring a multi-pronged approach. It involves transitioning away from fossil fuels towards renewable energy sources, such as solar, wind, and geothermal power. This transition demands significant investments in renewable energy infrastructure, technological innovation, and policy reforms that incentivize clean energy adoption. It also requires a shift in our energy consumption patterns, promoting energy efficiency and reducing our overall reliance on energy-intensive technologies. Beyond energy production, reducing emissions also requires addressing other sources of greenhouse gases, such as deforestation and agricultural practices. Protecting and restoring forests plays a critical role in absorbing atmospheric carbon dioxide, acting as a natural carbon sink. Sustainable agricultural practices, such as reducing methane emissions from livestock and improving soil health, are also crucial for mitigating climate change. These actions require collaborative efforts between governments, businesses, and individuals. Individual actions, while seemingly small, collectively contribute significantly to the reduction of greenhouse gas emissions. Simple changes in our daily lives, such as choosing public transportation, cycling, or walking instead of driving, adopting energy-efficient appliances, reducing our meat consumption, and minimizing waste, can make a tangible difference. These seemingly small actions, when combined with larger-scale policy changes and technological innovations, can create a powerful wave of change. The challenge of reducing emissions is substantial, but not insurmountable. The urgency of the situation demands immediate action, requiring a coordinated global effort to transition towards a sustainable future. The consequences of inaction are far too severe to ignore. By embracing sustainable practices, investing in clean energy technologies, and implementing effective policies, we can significantly reduce greenhouse gas emissions, slow the rate of ice melt, and safeguard the future of our planet's ice and its invaluable role in the global ecosystem. The time to act is now. While drastically reducing greenhouse gas emissions remains our paramount goal in combating climate change, we must also acknowledge the unavoidable impacts of ice melt already underway. This necessitates a parallel focus on adaptation strategies, proactive measures to prepare for and manage the consequences of a changing climate. It's not a question of choosing one approach over the other. Rather, it's about pursuing both mitigation and adaptation simultaneously for a comprehensive approach. One of the most pressing challenges is rising sea levels. Coastal communities, particularly those in low-lying areas, are particularly vulnerable. Developing robust coastal defenses is crucial for protecting these communities and their infrastructure. This involves implementing a range of measures, including building seawalls, restoring coastal wetlands, and implementing managed retreat strategies where appropriate. Seawalls, while effective in certain situations, can be costly and may have unintended environmental consequences. Restoring coastal wetlands, on the other hand, offers a more natural and sustainable solution, providing a buffer against storm surges and erosion. Managed retreat, though a challenging concept, may be necessary in some cases, involving the relocation of communities from increasingly vulnerable areas. Beyond coastal defenses, adapting to the impacts of ice melt also requires innovative strategies for managing water resources. Changes in precipitation patterns and glacier melt will affect river flows, impacting the availability of fresh water for drinking, agriculture, and industry. Developing water storage infrastructure, improving water management techniques, and promoting water conservation are essential for ensuring water security in a changing climate. This involves investing in dams, reservoirs, and water treatment facilities, as well as implementing efficient irrigation systems and water-saving technologies. Water conservation education and awareness campaigns are also crucial for promoting responsible water use. The melting of glaciers and ice sheets also has significant implications for ecosystems. Changes in freshwater availability and altered river flows can have cascading effects on aquatic habitats and biodiversity. Conservation efforts focusing on protecting vulnerable species and restoring degraded ecosystems are essential for mitigating these impacts. This includes establishing protected areas, implementing habitat restoration projects, and promoting sustainable fishing practices. The focus is on preserving biodiversity and ensuring the resilience of ecosystems in the face of climate change. Adapting to the impacts of ice melt requires a holistic approach, integrating various strategies to address the multifaceted challenges posed by a changing climate. This involves close collaboration between scientists, policymakers, engineers, and local communities, fostering a collective effort to build resilient communities and safeguard our planet's future. It's about proactively preparing for the challenges ahead, while simultaneously intensifying efforts to mitigate climate change and reduce greenhouse gas emissions. The success of our adaptation strategies will depend on our ability to anticipate future changes, develop innovative solutions, and implement them effectively. It's a shared responsibility, requiring collaborative efforts across the globe. The challenge of protecting our planet's ice and mitigating the impacts of climate change transcends national borders. It's a global issue demanding a unified, international response. No single nation, however powerful, can effectively address this challenge alone. The interconnectedness of our climate system means that the consequences of climate change are felt worldwide, regardless of where emissions originate. Rising sea levels, altered weather patterns, and ecosystem disruptions are global phenomena that demand global solutions. International cooperation is not merely a desirable goal. It's an absolute necessity. It requires collaborative efforts on multiple fronts, involving governments, scientists, businesses, and individuals from around the world. This cooperation takes many forms, from international agreements and treaties to collaborative research projects and technological advancements. The Paris Agreement, for example, serves as a landmark achievement in international climate cooperation. This agreement, signed by nearly every nation, sets a framework for reducing greenhouse gas emissions and limiting global warming. While the agreement represents a significant step forward, its success hinges on the commitment and collective action of all signatory nations. It requires ongoing monitoring, robust enforcement mechanisms, and regular reviews to ensure that countries are meeting their emission reduction targets. Beyond international agreements, collaborative research efforts are crucial for advancing our understanding of climate change and its impacts on ice formations. Scientists from various countries are working together to monitor ice melt, study the dynamics of glaciers and ice sheets, and develop improved climate models. Sharing data, expertise, and resources is essential for accelerating scientific progress and informing effective policy decisions. International cooperation also plays a vital role in developing and deploying clean energy technologies. The transition to a low-carbon economy requires technological innovations, and international collaboration can accelerate this process. Sharing technological know-how, fostering joint research ventures, and providing financial support for developing nations can facilitate the widespread adoption of renewable energy sources. This collective effort to transition towards clean energy is crucial for reducing greenhouse gas emissions and mitigating the impacts of climate change. Furthermore, international cooperation is essential for supporting vulnerable communities that are disproportionately affected by climate change. Providing financial assistance, technical expertise, and capacity-building programs to developing nations can help them adapt to the impacts of climate change and build resilience to future shocks. This support includes developing early warning systems for extreme weather events, investing in infrastructure that is resilient to climate change, and promoting sustainable development practices. The protection of our planet's ice and the mitigation of climate change are truly global endeavors, requiring sustained international cooperation and a shared commitment to a sustainable future. The challenge is immense, but the potential rewards, a healthier planet for future generations, are immeasurable. The time for collaborative action is now, to ensure a future where ice continues to play its crucial role in shaping our world. Technology plays a crucial, multifaceted role in our efforts to understand, monitor, and protect the world's ice formations. From sophisticated satellite imagery to advanced sensors deployed in remote locations, technological advancements are revolutionizing our ability to track changes in ice cover and predict future melt patterns. Satellite-based remote sensing provides a comprehensive overview of vast ice sheets and glaciers, allowing scientists to monitor changes in their extent, thickness, and surface velocity with unprecedented accuracy. These satellites utilize a variety of sensors, including radar altimeters, which measure the height of the ice surface, and optical sensors, which capture images of the ice's surface features. This data is then analyzed to detect subtle changes in ice mass balance, providing crucial insights into the rate of ice melt. In addition to satellite observations, ground-based monitoring networks are deployed in key locations to collect detailed measurements of ice properties. These networks include weather stations, GPS receivers, and automated sensors that continuously monitor temperature, snow accumulation, and ice flow. The data collected from these networks provides valuable ground truth information that can be used to validate and improve the accuracy of satellite-based observations. Beyond monitoring, technology is also playing a key role in developing sophisticated climate models that can predict future ice melt scenarios. These models incorporate a wide range of factors, including atmospheric and oceanic conditions, ice dynamics, and greenhouse gas concentrations. By incorporating data from satellite observations and ground-based measurements, these models can provide valuable insights into the potential impacts of climate change on ice formations. Moreover, technological innovations are being developed to explore potential strategies for protecting ice formations. These strategies include geoengineering techniques, such as artificial cloud brightening, which could reflect more sunlight back into space and reduce ice melt. While these techniques are still in the early stages of development, they offer a potential pathway to mitigate the impacts of climate change on ice formations. Furthermore, technological advancements are crucial in improving our understanding of the intricate processes that govern ice formation and melt. High-performance computing allows scientists to analyze vast datasets from satellite observations and ground-based measurements, revealing complex patterns and relationships that might otherwise be missed. This deeper understanding of ice dynamics is essential for improving the accuracy of climate models and informing effective conservation strategies. In conclusion, technology is not just a tool for monitoring ice. It's a powerful engine driving our efforts to understand, protect, and conserve this vital component of our planet's climate system. From satellite imagery to advanced climate models, technological innovations are essential for mitigating the impacts of climate change and safeguarding our frozen heritage. The ongoing development and deployment of these technologies are crucial in our collective fight to protect our planet's precious ice formations. Understanding the science of ice and the urgent threat of climate change isn't just for scientists. It's crucial for everyone. We all share this planet, and the fate of its ice directly impacts our collective future. Raising public awareness isn't simply about disseminating information. It's about fostering a deeper connection with the natural world and inspiring action. Imagine the breathtaking beauty of a snowflake, each one a unique crystalline masterpiece. Now, picture the immense power of a glacier, carving valleys and shaping landscapes over millennia. These seemingly disparate elements are interconnected, woven into the intricate fabric of our planet's climate system. Understanding this connection is the first step towards responsible stewardship of our environment. Effective public awareness campaigns must go beyond simply stating facts and figures. They need to evoke emotion, to connect with people on a personal level. Stunning visuals, compelling storytelling, and interactive experiences can all be powerful tools for engaging audiences and conveying the urgency of the situation. Think of documentaries showcasing the stunning landscapes of the Arctic or Antarctic, juxtaposed with the heartbreaking reality of melting ice and disappearing habitats. These images can resonate deeply, fostering a sense of empathy and responsibility. Educational programs targeting different age groups are essential. For younger audiences, engaging interactive exhibits and age-appropriate lessons can foster a love for science and cultivate environmental stewardship from a young age. For adults, workshops, lectures, and online courses can provide deeper insights into the science of climate change and its impacts on ice formations. These opportunities for learning should be readily accessible and tailored to different learning styles and preferences. The role of media in raising public awareness cannot be overstated. Documentaries, news reports, and social media campaigns can reach vast audiences and disseminate critical information about climate change and its consequences. However, it's crucial that this information is presented accurately, avoiding sensationalism or misinformation. Responsible journalism plays a vital role in informing the public and shaping public opinion. Furthermore, engaging with communities directly is essential. Local events, workshops, and community discussions can foster a sense of shared responsibility and empower individuals to take action. These initiatives can involve local experts, scientists, and community leaders, fostering a sense of collaboration and shared purpose. It's not just about awareness. It's about building a movement, a collective commitment to protecting our planet. Ultimately, raising public awareness about the science of ice and the impacts of climate change is not merely an educational endeavor. It's a critical step towards building a sustainable future. By fostering a deeper understanding and connection with the natural world, we can inspire individuals to take action and contribute to a global effort to protect our planet's precious ice formations. The future of our planet's ice, and indeed our own future, depends on it. Protecting our planet's ice isn't solely the responsibility of governments or large corporations. Each of us plays a vital role. While global cooperation is essential, individual actions, when multiplied, create a powerful wave of positive change. It's about recognizing that even small choices can collectively make a significant impact on our planet's future. Reducing your carbon footprint is the most impactful step you can take. This involves making conscious decisions about your energy consumption, transportation, and lifestyle choices. Consider switching to renewable energy sources like solar or wind power for your home. Opt for energy-efficient appliances and light bulbs, reducing your reliance on fossil fuels. Embrace public transport, cycling, or walking whenever possible, minimizing your reliance on cars. If you need to travel by air, explore options to offset your carbon emissions through reputable carbon offsetting programs. Beyond energy consumption, think about your diet. The food we eat has a significant environmental footprint. Reducing your meat consumption, especially red meat, can significantly decrease your carbon emissions. Choosing locally sourced, seasonal produce minimizes transportation distances and reduces the environmental impact associated with food production and distribution. Consider reducing food waste. Composting food scraps can also contribute to a smaller carbon footprint. Sustainable consumption is another key area. Before buying new products, consider whether you truly need them. Opt for durable, high-quality items over cheap, disposable ones. Support businesses committed to sustainable practices and ethical sourcing. Choose products with minimal packaging and prioritize recycling and proper waste disposal. These small changes can make a surprising difference in the long run. Advocacy and engagement are equally important. Support organizations working to protect our planet's ice and advocate for policies that address climate change. Educate yourself and others about the science of ice and the impacts of climate change. Engage in conversations with friends, family, and your community, spreading awareness and inspiring others to take action. Your voice matters, and your actions can inspire others to join the movement. By making conscious choices in our daily lives, we can collectively contribute to a more sustainable future. The seemingly small actions we take individually, when combined with collective efforts, can create a powerful force for change. Protecting our planet's ice requires a global effort, and every individual contribution, no matter how small, is a step in the right direction. Let's work together to safeguard our frozen heritage for generations to come. The fate of our planet's ice is inextricably linked to our future. The breathtaking beauty of glaciers, the intricate artistry of snowflakes, these are not just aesthetically pleasing aspects of our world. They are integral components of a delicate, interconnected system. The melting of these frozen landscapes represents more than just a loss of scenic wonder. It signifies a profound disruption to the Earth's climate and ecosystems. Rising sea levels, driven by melting glaciers and polar ice caps, pose a direct threat to coastal communities worldwide. The displacement of populations, the loss of infrastructure, and the increased vulnerability to extreme weather events are not distant possibilities. They are already unfolding realities. The disruption of ocean currents, crucial for regulating global temperatures and distributing nutrients, further underscores the severity of the situation. These currents, influenced by the melting of polar ice, are vital for maintaining the delicate balance of our planet's climate. Beyond the immediate consequences, the loss of ice threatens biodiversity. Unique ecosystems, adapted to the harsh conditions of polar regions and high-altitude glaciers, are facing extinction. The polar bears, the penguins, the countless species that call these icy environments home, are facing an existential threat. The loss of these species is not only a tragedy in itself, it disrupts the intricate web of life, impacting the entire planet. The urgency of the situation cannot be overstated. The scientific evidence is overwhelming, pointing towards the dire consequences of inaction. We have the knowledge, the tools, and the capacity to address this challenge. But knowledge is only power when it is translated into action. We need to move beyond awareness and into decisive collective action. The future of ice, and indeed the future of our planet, depends on our collective commitment to mitigating climate change. This requires a multifaceted approach, encompassing international cooperation, technological innovation, and individual responsibility. Governments must implement robust policies to reduce greenhouse gas emissions, investing in renewable energy sources and promoting sustainable practices. Scientists must continue their crucial work in monitoring ice formations, improving climate models, and developing innovative solutions. But the responsibility does not rest solely on governments and scientists. Each of us has a crucial role to play. By making conscious choices in our daily lives, reducing our carbon footprint, supporting sustainable businesses, and advocating for climate action, we can contribute to a more sustainable future. We must remember that our actions, however small they may seem, collectively create a powerful force for positive change. Let us embrace our shared responsibility and work together to protect our planet's precious ice for generations to come. The time for action is now. The future of our frozen world depends on it. Imagine Earth as a vast, intricate machine, its parts delicately balanced, each impacting the others in a complex dance of cause and effect. Ice, far from being a passive element, plays a crucial role in this intricate machinery, its influence extending far beyond its frozen landscapes. Understanding the interconnectedness of ice with other Earth systems is crucial to grasping the far-reaching consequences of its loss. Let's start with the oceans. Vast ice sheets and glaciers act as colossal reservoirs of freshwater, influencing global sea levels and ocean currents. The melting of these ice giants disrupts this delicate balance, causing sea levels to rise, threatening coastal communities and ecosystems. Furthermore, the influx of freshwater from melting ice alters ocean salinity and temperature, disrupting the intricate currents that regulate global climate patterns. These currents, like a planet-sized conveyor belt, distribute heat around the globe, influencing weather systems and regional climates. Disrupting them throws this vital system out of balance. Moving to the atmosphere, ice plays a vital role in regulating global temperatures. Vast ice sheets reflect sunlight back into space, helping to cool the planet. As these reflective surfaces shrink, the Earth absorbs more solar radiation, leading to a warming effect, a feedback loop that accelerates further ice melt. This process isn't confined to polar regions. Changes in ice cover at higher altitudes also impact atmospheric circulation patterns, influencing weather systems worldwide. Changes in snowfall and rainfall patterns are linked directly to variations in ice cover and glacial melt. The impact on terrestrial ecosystems is equally profound. Glaciers and ice caps are vital sources of fresh water for rivers and streams, sustaining life in downstream ecosystems. As glaciers retreat, these water sources diminish, impacting agriculture, drinking water supplies, and biodiversity. The loss of ice also alters landscapes, impacting habitats and leading to the displacement or extinction of species adapted to cold environments. The ripple effect extends far beyond the immediate vicinity of the melting ice. The interconnectedness of ice with Earth systems is undeniable. It's a delicate balance, and the disruption caused by ice loss reverberates across the planet, affecting everything from sea levels and ocean currents to atmospheric circulation and terrestrial ecosystems. Understanding this interconnectedness highlights the urgency of addressing climate change. Protecting our planet's ice is not just about preserving scenic beauty. It's about safeguarding the stability and resilience of the entire Earth system. The consequences of inaction are far-reaching and profoundly impactful, affecting every aspect of life on Earth. We've journeyed through the science of ice, from the microscopic dance of water molecules forming intricate snowflakes to the colossal power of glaciers shaping landscapes over millennia. We've explored the intricate beauty of ice crystals, the breathtaking vistas of frozen landscapes, and the vital role ice plays in regulating our planet's climate. But beyond the scientific facts and figures lies a deeper appreciation for the profound beauty and power of ice. Think of the delicate, ephemeral beauty of a snowflake, each one a unique masterpiece of nature's artistry. Imagine the awe-inspiring majesty of a glacier, a slow-moving river of ice carving its way through mountains, a testament to the power of nature's relentless forces. These are not just scientific phenomena. They are sources of wonder and inspiration, evoking a sense of awe and respect for the natural world. The power of ice is both subtle and immense. The delicate balance of ice sheets and glaciers influences global sea levels, ocean currents, and weather patterns. The seemingly insignificant melting of a single snowflake contributes to the larger pattern of climate change, a reminder of the interconnectedness of all things. But this power is not something to be feared. It's something to be understood and respected. Ice is a powerful symbol of resilience and adaptation. Life thrives in the harshest icy environments, a testament to the tenacity of nature. The organisms that call these icy realms home are a testament to the remarkable adaptability of life. They remind us that life finds a way, even in the most challenging conditions. Their survival depends on the preservation of their icy habitats. The loss of ice is not just an environmental tragedy. It's a loss of beauty, power, and inspiration. It's a loss of a vital component of our planet's intricate system. It is a loss that impacts us all. The challenges we face in protecting our planet's ice are significant, but they are not insurmountable. By understanding the science, appreciating the beauty, and acknowledging the power of ice, we can work together to ensure that future generations can experience the wonder and awe of a world where ice continues to play its vital role. Let us strive to preserve this remarkable substance for the benefit of all life on Earth. Let the beauty and power of ice inspire us to act, to protect, and to preserve. Let's recap our exploration of ice formation, a process as diverse and fascinating as the icy landscapes it creates. We've seen how the seemingly simple act of water freezing into ice is actually a complex interplay of temperature, pressure, and the unique properties of water molecules themselves. Remember those hydrogen bonds? They're the key. First, we looked at snowflakes, those exquisite six-sided wonders. Their formation begins high in the atmosphere where water vapor, clinging to microscopic particles, crystallizes around a nucleus. As more water vapor freezes onto this initial crystal, it grows, developing its iconic six-fold symmetry, a testament to the underlying order of the molecular structure. Each snowflake is unique, a testament to the countless variations in atmospheric conditions during its formation. Then we moved on to the formation of sea ice, a different story altogether. This type of ice forms directly from the freezing of seawater, a process influenced by salinity and temperature. As seawater cools, the salt is initially expelled, resulting in a slightly less salty ice than the surrounding water. This process leads to the formation of a complex structure with brine pockets trapped within the ice, affecting its physical properties and influencing its role in ocean dynamics. Glaciers, those majestic rivers of ice, form through a different mechanism entirely. They begin as accumulating snow, gradually compacting under its own weight. As the snow compresses, the air is squeezed out, and the individual snowflakes transform into denser, granular snow called firn. Over time, the firn continues to compact, eventually forming glacial ice, a solid mass of interlocking ice crystals. This process can take centuries, resulting in the immense ice sheets and glaciers we see today. Finally, we considered the formation of ice in lakes and rivers. Here, the process is relatively straightforward, driven primarily by the decrease in temperature. As the water cools below freezing point, ice crystals begin to form at the surface, growing outward and downward until the entire water body is frozen. The resulting ice is generally clearer and less complex than sea ice or glacial ice, although its thickness can vary significantly depending on environmental factors. Each type of ice, whether a delicate snowflake, a vast glacier, or a frozen lake, holds a unique story of its formation, a reflection of the specific environmental conditions that shaped it. Understanding these diverse formation processes is crucial to appreciating the full complexity and importance of ice in Earth's systems. Let's turn our attention to the remarkable role ice plays in supporting life on Earth. It's not just a beautiful and powerful force of nature. It's a vital component of countless ecosystems, providing habitat, sustenance, and a foundation for a surprisingly diverse array of life forms. Consider the polar regions, where vast expanses of sea ice form a crucial habitat for a plethora of species. Ice algae, microscopic plants living within the ice itself, form the base of the food web, supporting krill, which in turn nourish larger animals like seals, penguins, and polar bears. These iconic animals are not just symbols of the Arctic and Antarctic. They are integral parts of complex ecological systems intricately linked to the presence and extent of sea ice. The timing of sea ice melt and freeze significantly influences their breeding cycles, migration patterns, and overall survival. Moving to freshwater ecosystems, we find that ice cover plays a crucial role in maintaining the delicate balance of aquatic life. During winter, ice acts as an insulator, protecting lakes and rivers from extreme temperature fluctuations and preventing complete freezing. This allows aquatic organisms to survive harsh winter conditions, providing a refuge from freezing temperatures and maintaining a degree of ecological stability. The spring melt provides a crucial influx of nutrients, triggering the growth of phytoplankton and supporting the entire food web. Glacial ecosystems, though seemingly barren, support surprisingly diverse communities of organisms adapted to the extreme conditions. These specialized creatures thrive in meltwater streams and on the glacier surfaces themselves, forming unique food webs that are remarkably resilient, despite the harsh conditions. The meltwater also plays a critical role in sustaining downstream ecosystems, providing a source of fresh water and nutrients for a variety of plants and animals. Even beyond these specific ecosystems, ice plays a broader role in regulating global climate patterns. The reflectivity of ice, or its albedo, influences the amount of solar radiation absorbed by the Earth, impacting global temperatures and weather patterns. This, in turn, affects the distribution and abundance of species across the globe. The intricate relationship between ice and life highlights the profound interconnectedness of Earth's systems. The loss of ice is not simply a reduction in a beautiful natural resource. It's a disruption to the complex web of life that depends on its presence. The consequences of this disruption will ripple through ecosystems worldwide, impacting biodiversity, food security, and the stability of our planet as a whole. Understanding this interconnectedness is critical to developing effective strategies for conservation and protecting the future of life on Earth. The fate of these ecosystems, and indeed the planet, is inextricably linked to the fate of ice. Imagine drilling deep into a glacier, extracting a cylinder of ancient ice, a time capsule preserving millennia of Earth's history. That's the power of ice cores, offering us a remarkable window into the past, revealing details about past climates and environmental changes with unparalleled precision. These seemingly simple cylinders of ice are actually incredibly complex archives. As snow accumulates and compresses into ice, it traps tiny air bubbles, dust particles, pollen, volcanic ash, and even the remnants of ancient organisms. These trapped materials provide a wealth of information about the atmospheric composition, temperature, precipitation patterns, and even volcanic activity at the time the snow fell. By analyzing the chemical composition of the ice and the air bubbles trapped within, scientists can reconstruct past climates with remarkable accuracy. The isotopic ratios of water molecules within the ice, for example, provide a direct measure of past temperatures. Higher ratios of heavier isotopes indicate colder temperatures, while lower ratios suggest warmer conditions. This allows scientists to build detailed temperature records stretching back hundreds of thousands of years, revealing patterns of climate change long before humans began recording weather data. The analysis of trapped air bubbles is equally revealing. These bubbles contain samples of the ancient atmosphere, allowing scientists to measure the concentrations of greenhouse gases like carbon dioxide and methane over time. This data provides invaluable insights into the natural variability of these gases and helps scientists understand the impact of human activities on the current atmospheric composition. Beyond greenhouse gases, ice cores also contain valuable information about past volcanic eruptions. Volcanic ash layers within the ice provide a precise timeline of eruptions, allowing scientists to correlate these events with climate changes. The chemical composition of the ash can also reveal the type of volcano and the intensity of the eruption. Similarly, the presence of pollen and other organic matter provides information about past vegetation and ecosystem changes. The analysis of these materials gives us a comprehensive picture of past environments. The insights gleaned from ice cores have fundamentally reshaped our understanding of Earth's climate history, revealing long-term trends, natural variations, and the impact of human activities on the planet. These records show us that Earth's climate is inherently dynamic, but also highlight the unprecedented rate of change we are currently experiencing. This understanding underscores the urgency of addressing climate change and the importance of protecting these invaluable archives for future generations. The information locked within these ancient ice cores is not just a glimpse into the past. It is a crucial guide for shaping a sustainable future. The melting of ice, a process seemingly simple at first glance, is in reality a complex phenomenon with far-reaching and profound consequences for our planet. It's not just about the disappearance of beautiful glaciers or the shrinking of Arctic sea ice. It's about a cascade of interconnected effects that ripple through Earth's systems. At its most basic level, ice melting is a phase transition, a change from the solid state to the liquid state. This occurs when the temperature of the ice rises above its melting point, causing the ice crystals to break their rigid structure and transition into water. However, the rate at which this melting occurs is influenced by several factors, including air temperature, water temperature, solar radiation, and even wind speed. The consequences of this melting are dramatic and multifaceted. Perhaps the most immediate and widely recognized impact is the rise in sea levels. As glaciers and ice sheets melt, the vast quantities of stored freshwater flow into the oceans, causing a global increase in sea level. This poses a significant threat to coastal communities and ecosystems worldwide, leading to increased flooding, erosion, and saltwater intrusion into freshwater sources. Beyond sea level rise, melting ice significantly impacts weather patterns. The reflectivity of ice, its albedo, plays a crucial role in regulating global temperatures. As ice melts, the darker surfaces exposed absorb more solar radiation, leading to a positive feedback loop where further warming accelerates melting. This altered albedo can disrupt atmospheric circulation patterns, potentially leading to more extreme weather events such as heat waves, droughts, and intense storms. The ecological consequences of ice melt are equally profound. The loss of sea ice disrupts the delicate ecosystems of the polar regions, threatening the survival of countless species that depend on it for habitat, food, and breeding grounds. Similarly, the melting of glaciers and snowpack affects freshwater resources, impacting downstream ecosystems and the availability of water for human consumption and agriculture. The melting of ice is not merely an environmental issue. It is a complex interplay of physical, chemical, and biological processes with far-reaching consequences for human societies. Understanding the intricate mechanisms behind ice melt and its impacts is crucial for developing effective strategies to mitigate climate change and adapt to the unavoidable changes that are already underway. The future of our planet depends on our ability to address this challenge effectively. The science of melting ice is, therefore, not just a fascinating area of scientific inquiry. It is a crucial piece of the puzzle in understanding and addressing one of the most pressing challenges of our time. From ancient myths to modern art, ice has captivated human imagination for millennia. Its ethereal beauty, its transformative power, and its inherent fragility have inspired countless stories, poems, paintings, and sculptures across diverse cultures. Let's explore the profound cultural significance of ice. In many cultures, ice is associated with purity, cleansing, and renewal. The pristine beauty of a snowflake, a microcosm of intricate design, is a testament to nature's artistry. This inherent beauty has been captured by artists throughout history, from delicate watercolor paintings of icy landscapes to breathtaking photographs of frozen waterfalls. The symbolism of ice often reflects its ability to transform and regenerate, a frozen world that melts and renews, mirroring cycles of life, death, and rebirth. Mythology often features ice as a powerful and sometimes fearsome force. In Norse mythology, for example, the realm of frost giants and icy landscapes represents a realm of primordial power and chaos. In other cultures, ice is associated with divine beings or spirits, embodying the power of nature and the forces of winter. These myths reveal a deep-seated human awareness of the power and mystery inherent in ice, its ability to shape landscapes and influence human lives. Literature frequently utilizes ice as a metaphor. The coldness of ice can represent emotional detachment, isolation, or the harshness of reality. Conversely, the thawing of ice can symbolize hope, renewal, and the overcoming of adversity. Authors have used ice as a powerful symbol to explore themes of transformation, resilience, and the cyclical nature of life. The cultural significance of ice extends beyond its artistic and literary representations. Many cultures have developed unique traditions and practices related to ice, from ice skating festivals and winter carnivals to the art of ice sculpting and the use of ice in traditional ceremonies. These practices reflect a deep connection between humans and the natural world, demonstrating how ice has shaped human culture and social interactions throughout history. The cultural significance of ice is a testament to its enduring power to inspire, awe, and challenge us. Its beauty, its power, and its fragility serve as a constant reminder of the delicate balance of nature and the importance of protecting this precious resource for future generations. From ancient myths to contemporary art, ice continues to hold a special place in the human heart and imagination, a testament to its profound cultural significance. The stories we tell about ice, the art we create inspired by it, and the traditions we develop around it reflect a deep-seated human connection to this remarkable substance. The future of ice is inextricably linked to the fate of our planet. The current rate of ice melt, driven primarily by climate change, presents a stark and urgent challenge. We're not just talking about a gradual shrinking of glaciers. We're facing a potentially catastrophic cascade of events with far-reaching consequences. Rising global temperatures are accelerating the melting of glaciers and ice sheets at an alarming rate. This contributes significantly to rising sea levels, threatening coastal communities and ecosystems worldwide. Low-lying islands and coastal cities face the risk of inundation, displacement, and the loss of vital infrastructure. The consequences extend beyond immediate flooding, impacting freshwater resources, agricultural productivity, and human health. The melting of Arctic sea ice has profound implications for global weather patterns. The loss of reflective ice surfaces leads to increased absorption of solar radiation, further amplifying warming and creating a dangerous feedback loop. This can result in more frequent and intense extreme weather events, including heat waves, droughts, and powerful storms, affecting regions far beyond the polar regions. The ecological consequences are equally devastating. The loss of sea ice and glacial melt disrupts delicate ecosystems, threatening the survival of numerous species adapted to these unique environments. Polar bears, penguins, and countless other creatures face habitat loss, reduced food sources, and increased competition for dwindling resources. The disruption of marine food webs has cascading effects throughout the global ecosystem. Beyond the direct impacts of melting ice, there are significant economic and social ramifications. Coastal erosion and flooding can cause billions of dollars in damages, displacing populations and disrupting economic activity. Changes in weather patterns can impact agriculture, fishing, and tourism, leading to economic hardship and social unrest. Addressing this challenge requires a multifaceted approach. Reducing greenhouse gas emissions through a global transition to renewable energy sources is paramount. Simultaneously, we need to invest in adaptation strategies to help communities cope with the unavoidable impacts of climate change, including sea level rise and extreme weather events. Protecting and restoring vulnerable ecosystems, including those dependent on ice, is crucial for preserving biodiversity and maintaining the resilience of our planet. The future of ice is not predetermined. While the challenges are significant, our collective actions can still make a difference. By embracing sustainable practices, investing in innovative technologies, and fostering global cooperation, we can mitigate the worst impacts of climate change and secure a more sustainable future for both humanity and the planet's precious ice formations. The urgency of the situation demands immediate and decisive action. The future of ice, and indeed the future of our planet, depends on it. As we conclude our journey into the fascinating world of ice, let's reflect on the profound responsibility we bear towards this magnificent, yet fragile, element of our planet. The breathtaking beauty of ice, from the intricate patterns of snowflakes to the awe-inspiring grandeur of glaciers, is a testament to nature's artistry. But this beauty is under threat. The rapid melting of ice formations, driven by climate change, is not merely an environmental concern. It's a crisis impacting every facet of human life and the intricate web of life on Earth. The science is clear. Our actions are altering the planet's climate at an unprecedented rate. The consequences are visible in the shrinking glaciers, the thawing permafrost, and the rising sea levels. These are not abstract concepts. They represent tangible losses: the loss of biodiversity, the loss of cultural heritage, and the loss of homes and livelihoods for millions of people around the world. We are witnessing the unraveling of ecosystems that have taken millennia to develop, and the consequences will be felt for generations to come. The cultural significance of ice, deeply woven into the fabric of human societies for centuries, is also at risk. The stories, traditions, and artistic expressions inspired by ice are an integral part of our shared heritage. Losing this heritage would be a profound loss, not just for those directly affected, but for the entire human family. The melting of ice represents the erosion of a cultural legacy as much as it represents the erosion of our planet's physical landscape. But despair is not the answer. While the challenges are immense, the potential for positive change is equally vast. We have the knowledge, the technology, and the collective power to mitigate the worst impacts of climate change and to protect our frozen heritage for future generations. This requires a fundamental shift in our approach, a transition away from unsustainable practices and towards a future powered by renewable energy, sustainable consumption, and responsible resource management. The preservation of ice is not just about saving glaciers and polar ice caps. It's about safeguarding the future of our planet. It's about ensuring the stability of our climate, protecting biodiversity, and maintaining the well-being of human societies. It's about ensuring that future generations can experience the wonder and beauty of a world with ice, just as we have. This requires a global effort, a collective commitment to act. It demands collaboration between governments, businesses, and individuals. A shared responsibility to reduce our carbon footprint, invest in sustainable solutions, and advocate for policies that protect our planet. It's a call to action, a call to protect not just the ice, but the future of life on Earth. Let us rise to this challenge, and together, safeguard our frozen heritage for generations to come. The future of ice is in our hands.